We're now going to turn our attention to more addition reactions to pi bonds. And we're going to begin with the addition of halogens to alkenes. Generically, alkene reacting with X2 produces what's known as a vicinal dihalide. From a practical point of view, the reaction occurs quite well with bromine or chlorine, sometimes with iodine. Fluorine is never used for this reaction. The reaction is stereoselective, and we'll talk more about the manner in which we observe that. And as I noted, we produce these so-called vicinal dihalides. Vicinal is a term that simply means on adjacent carbons. Two simple examples. Here we have the reaction of chlorine with ethylene to produce 1,2-dichloroethane. And here's a very instructive example. We have cyclopentene. Hydrogens here on the double bond are shown just so we can see what happens in the product. This happens in solution. A solution of bromine and carbon tetrachloride, very common solvent for these reactions. And you'll notice here we produce a 1,2-dibromide, but we should note the stereochemistry. The bromines have a trans relationship on the new cycloalkane ring. Before we go further, I should mention that historically the reaction of bromine was used as a qualitative test for the presence of alkenes because this reaction is so rapid and produces a color change. If you take an ordinary alkane, here we have cyclopentane, and you mix it with a bromine solution, typically this is done in carbon tetrachloride as a solvent, the bright red color of bromine persists because there's no reaction. Elemental bromine has the color of blood. But if an alkene is present, the bromine will react quite rapidly with the alkene and produce the dibromide product. These products are typically colorless. And so there's a dramatic color change from blood red to colorless, indicating the presence of an alkene. This is still used today as a quick qualitative test. If you have a sample, you know it's a hydrocarbon, you want to know whether there's an alkene present, you add a couple drops of bromine and determine whether it will decolorize that bromine. The addition of halogens to alkenes is stereospecific in that if you have a substrate such as cycloalkanes like cyclopentane shown here, you will invariably produce the trans product and you do not observe the cis product. So you only get the so-called anti-addition. It's called anti-addition because you end up with the bromines added to essentially opposite faces of the double bond. One curious feature of the mechanism of these reactions is that there's no evidence to support the presence of a carbocation intermediate, a positively charged carbon. Some of these experiments involve using substrates that are prone to rearrangement should carbocations form. We've seen this substrate before in our examination of carbocation rearrangements because electrophilic additions to the double bond typically produce a secondary carbocation, and we observe rapid alkyl shifts and products of those alkyl shifts. In this case, reaction with bromine produces only the 1,2-dibromide that we see here. Now that doesn't disprove the presence of a carbocation, but it's strong evidence because the alkyl shift is an intramolecular reaction that should be much more rapid than the addition of the second bromine. And so the fact that we do not observe these sorts of products is in strong evidence that there isn't a discrete carbocation intermediate in the reaction. Another strong piece of evidence that a carbocation is not an intermediate in these reactions is the observation that we exclusively get anti-addition and that we get no what's called syn addition to the same face of the double bond. If a carbocation were a discrete intermediate, so imagine a mechanistic pathway where the double bond acts as nucleophile on the halogen, we add one bromine producing a carbocation intermediate. Carbocations, because of their planar structure, can undergo nucleophilic attack from either face. This should lead to a mixture of products should the carbocation exist. Again, we don't observe any syn addition, we only observe anti-addition. So there must be some other mechanistic pathway. The The most plausible explanation is the formation of a bridged intermediate of the type that's shown here. This mechanistically occurs by the electron rearrangement indicated in this step, a concerted addition of bromine to the double bond with pi electrons adding back to the bromine and loss of bromide ion. The result is a three-membered ring with a positive charge on the halogen. Generically, these are called halonium ions. The second step of the process is effectively an SN2, where bromide ion does a substitution from the backside of a carbon-bromine bond. Here, the HOMO-LUMO interaction is the pair of electrons from bromine in the HOMO of the bromide ion, adding into the antibond of the carbon-bromonium ion bond. The net result is that the bromine that was initially added remains attached to one face of the double bond. The bromide ion adds to the opposite face, and we only observe that anti-addition. Let's work through this mechanism step by step. The first step in the process is the formation of the bromonium ion intermediate, where we get nucleophilic attack and then kind of back bonding from one bromine with a loss of bromide ion. This adds a bromine atom in the form of a bromonium ion to one face of what was the double bond. This is followed by a nucleophilic attack of bromide ion from the opposite face of the bromonium ion. Now, this symmetrical compound that we have here can undergo addition to either carbon that the bromonium ion is bonded to. So we can add to the carbon there on the bottom of that structure and also add to the carbon on the top of the structure. The result is an enantiomeric mixture of vicinal dibromides. If bromine adds to the bottom from the back face, it ends up down, leaving the bromonium ion bromine up. And alternatively, if the bromide ion adds to the other carbon, it would be down, and the other carbon would be up. And the relationship between those two structures is that they are enantiomers. The choice of solvent is critically important in these halogenation reactions. If you carry out the reactions such as the previous examples in inert solvents like carbon tetrachloride or dichloromethane, you get reaction exclusively with the halogen and form the vicinal dihalide. But if you carry out the reaction in a nucleophilic solvent, even a weakly nucleophilic solvent like water or an alcohol, what you find is the predominant products are those reactions where the halonium ion forms, but the nucleophilic ring opening of the halopian ion happens by attack of the solvent, and we get products of that. And so in water, we produce products such as this one, which is generically known as a halohydrin. This would be a bromohydrin, where we have a bromine and hydroxyl group on adjacent carbons. And if you carry out the reaction in alcohol solvents, you produce products such as this, where we produce a new ether functional group on a carbon adjacent to the carbon that bears the halogen. Water and alcohols are slightly weaker nucleophiles than halide ions, but they're so abundant in these reaction systems because they're being used as solvent that we see virtually no dihalogenation. Here we work out the mechanism for the reaction of an alkene with chlorine in water as a solvent. The reaction begins in the usual fashion with the formation of the chloronium ion three-membered ring. But water, because it's weakly nucleophilic and very abundant in the reaction system, is the main nucleophile. And so again in an SN2 fashion, it undergoes backside attack on the halonium ion, opening the ring. This, of course, can happen to the other carbon of the halonium ion ring. Because it's adding from the back, the new oxonium ion is down in the stereochemistry of this structure. The chlorine is retained in its up position. And the reaction is completed by deprotonation of the oxonium ion by the solvent. And we ultimately produce the trans halohydrin and its enantiomer, which we haven't drawn. When the reaction with the halogen occurs in a nucleophilic solvent like water or an alcohol, then regiochemistry comes into play. And the outcome of that can be shown in these two examples that we see here. These are both unsymmetrical alkenes in that one end of the double bond has more carbons attached to it than the other does. For instance, this is a tertiary carbon, this is a primary carbon. In the example below, we have a tertiary carbon and a secondary carbon. The observation is that when these reactions occur, we end up with the halogen attached to the less substituted carbon, and the solvent is reacting at the more substituted carbon center. We can figure out why we get the regiochemistry by looking again at the mechanism, but now of an unsymmetrical alkene. So here we have the beginnings of the mechanism for the reaction of this methylcyclopentene with bromine in the presence of water. Again, the reaction begins by the formation of that bromonium ion. If we look at that bromonium ion more closely, we can draw some resonance structures of it. And those structures look like this. We have our original bromonium ion with the three-membered ring and the positive charge on bromine, and that is the dominant structure. That's the most stable form that we have here. It has more bonds than the others do. But these minor contributors are really informative, because you notice what I've done is simply move a pair of electrons onto bromine, leaving a carbocation in each of the structures. This corresponds to a tertiary carbocation, this one to a secondary. So in our resonance picture of the distribution of charge, if we're interested in the charge on these carbon atoms, the conclusion we would draw is that there is probably a greater proportion of positive charge on that tertiary carbon than there is on this secondary carbon. So when nucleophilic attack occurs, the greatest electrostatic attraction is, somewhat ironically, on the more substituted carbon. From here, the reaction will proceed by nucleophilic attack at that more positively charged carbon, which happens to be the more substituted carbon. That nucleophilic attack from the backside is going to push the methyl group up, as shown in this configuration, and we end up with the hydroxyl group bonded on the opposite face of the bromine. And once again, the final step is deprotonation of the oxonium ion to give our halohydrin, where the hydroxyl and bromine are anti. We'll finish our look at the addition of halogens by looking at the addition of halogens to alkynes. This is a less common reaction, has less synthetic usefulness. You can add one or two equivalents of halogen to an alkyne because of the presence of the two pi bonds. If you restrict the reaction to one equivalent of halogen, you produce vicinal divinyl halides. And if you add an excess of halogen, you can get two equivalents added and you end up forming these tetrahalo products. If you look at this first example, you can see that there's probably something going on here that isn't as mechanistically clean as what we saw with simple alkenes. You'll notice here that we produce 72% of this trans dibromide, but we produce a significant amount of this cis dibromide. So we're getting anti and we're getting syn addition. So it's a little confusing about what's going on in the mechanism of the reaction. Um, the second example is just an indication of the types of products that we form if we add an excess of halogen. Even though it isn't indicated here, this particular example used a vast excess of chlorine, so there was more than one equivalent there. Not only is the addition of halogen to alkynes less synthetically useful, it's also a bit of a puzzle for organic chemists. The mechanism of the addition is not well understood, even at this point. Trans dihalide predominates, which suggests that we get some halonium ion, but we get a significant amount of cis dihalide. So that suggests that perhaps a halonium ion isn't exactly what's involved. And for that matter, if you did form a halonium ion, there would be a double bond in that three-meter ring, and you would expect that to be particularly unstable and suffer from a great deal of angle strain. One other thing we can say is that alkynes are not as reactive as alkenes in these halogenation reactions. So much so that if you control the stoichiometry, you can get the reaction of an alkene in the presence of an alkyne, and the alkyne remains unreacted. And that's shown in this example here. If this ene-ine compound is subjected to 1 equivalent of bromine at low temperature, you get very clean dibromination of the double bond and no reaction of the triple bond.